Welcome back to the course entitled Elementary Electrochemistry. In today's class, we are going to discuss some of the applications of conductance measurement and also the EMF measurements. We are now almost towards the end of this course, so I will briefly discuss a couple of methods for determination of physical properties. So, we want to talk today about the determination of solubility product using conductometry, right? So, what do we know about sparingly soluble salts? These sparingly soluble salts are technically immiscible or insoluble in water. So, when you try to mix something like barium sulfate or silver chloride or strontium sulfate etc. in water and stir for a very long time, a very small amount of that salt will dissolve in water and make the solution conducting. So, the saturated solution of salts like barium sulfate, strontium sulfate, silver halides like I would say I should write as AX, where X equal to chlorine, bromine and iodine. The saturated solution of salts like these compounds have very low concentration of the ions of the salt. So, these solutions can be considered to be at infinite dilution. Therefore, the concentration of the ions, which in general is written as C, can be considered as the solubility of the said salt, right? Now, if LH2O is the specific conductance of pure water, we have discussed about this water because this water is also called conductivity water. which is of course prepared by multiple times distillation of water and then passing that water through ion exchange columns to remove any residual ions, so that you have very minimal ions dissociated from water, which corresponds to the degree of dissociation of water. So, this LH2O is very small, but it is a particular quantity. This is a value of specific conductance for such a pure water can be determined. And if Ls is the specific conductance of saturated solution of BaSO4 or any such salt. How do we make that saturated solution? Then we first take a large quantity, large excess of conductivity water, add a pinch of solid barium sulfate or silver chloride or silver nitrate to that, and start that suspension for a sufficiently long time, maybe 24 hours. Whatever amount of salt dissolves in that makes it a saturated solution of barium sulfate or silver chloride or silver iodide or strontium sulfate, whatever it is, and then we let the salt precipitate, whatever has undissolved, and we use the supernatant liquid for further measurement. So, then the equivalent conductance of say BaSO4 can be calculated as lambda equal to Ls minus L water divided by C into 1000, where C is the concentration of BaSO4, which is again equivalent to S, the solubility of BaSO4. So, one can write lambda equal to Ls minus L water by S into 1000, and this lambda also can be written as lambda 0, as this solution is equivalent to a solution at infinite dilution. That is why lambda can be written equal to lambda 0, right. So, now what do we know? We know that lambda 0 can be written as L0C plus L0A. Therefore, the solubility, the value of solubility can be calculated by Ls minus L water divided by Lc0 plus La0 into 1000 in gram equivalent per liter unit. To this, if you multiply by molecular weight of BaSO4 into this quantity, then it becomes grams per liter unit in terms of solubility in terms of grams per liter unit. So, let us see this using a particular problem. if the specific conductance of a saturated solution of strontium sulfate is 1.5 into 10 to the power minus 4 and that of pure water is 1.5 into 10 to the power minus 6 mole centimeter inverse, then at 25 degree centigrade calculate solubility of SrSO4 in grams per liter unit. So, what we should do? We should do S equal to LS, which is 1.5 into 10 to the power minus 4, which is 150 into 10 to the power minus 6 minus 1.5 into 10 to the power minus 6 mole centimeter inverse divided by the lambda 0, that is LC0 plus LA0 into 1000. So, now one has to find these values from the textbook in the table for the limiting ion conductances for strontium and sulfate, and when you find those values you would see that they are 59.2 and 79.8 and when you apply those values and do the calculation, you will end up getting 1.07 into 10 to the power minus 3 gram equivalent per liter. So, now this quantity has to be multiplied by the molecular weight of strontium sulfate. So, when you multiply this by m, you end up getting 92 the molecular weight of strontium sulfate is 92.8 into 1.07 into 10 to the power minus 3 grams per liter. So, that you can get is 0.099 grams per liter. So, when this is the solubility of barium sulfate, one can calculate the solubility product, which in this case is S square. So, you can simply multiply this by this and get the value of solubility product for strontium sulfate. So, this is how one can use the method of conductometric measurements for determination of solubility product. So, in this experiment what we need to do, we need to determine the specific conductance of a saturated solution of strontium sulfate, take the specific conductance of pure water from the standard table, take the values of LC and LA0 from the standard table and calculate the solubility of strontium sulfate. In the same way, one can determine the solubility product from EMF measurements. So, here let us use AgCl as the sparingly soluble salt and form a suitable cell using AgCl, and then couple this cell with a standard calomel electrode and determine the EMF of the cell. So, what we do? We take a 0.1 molar KCl solution. So, to a solution of 0.1 molar KCl for whom the value of F is 0.77, a few drops of AgNO3 is added. What will happen? When you have large excess of chloride ion in a solution like 0.1 molar KCl, you are adding 1 or 2 drops of silver nitrate solution. Almost all silver nitrate subsilver ions will form its chloride salt and get precipitated, and very small amount of silver plus ion will remain in solution, as we indicate it will indicate the solubility of that particular salt. Then a silver rod is dipped in the solution to act as an electrode. So, what we have is a silver electrode, silver solid as electrode. In this chamber we have 0.1 molar KCl, which is saturated with AgCl, which came from AgNO3, a couple of drops of AgNO3, and then this half cell is coupled with the Ag2Cl2 aqueous with Ag liquid, which corresponds to the calomel electrode. Whose E0 value is 0.049. .0494 volt at 25 degrees centigrade. So, now using our previous understanding of EMF of a cell, one can write E cell equal to EAG AgCl minus E calomel, right? I am sorry, it's a the EMF of calomel electrode is minus 0.3338 volt. So, now when we have constructed this cell, one can determine the E cell using a potentiometer, and suppose the E cell that we get from the potentiometer turns out to be 0.0494 volts, and EAG is not known, and E calomel, which is minus that, when you write here it will become 0.3338, both in terms of volt. So therefore AgAgCl will turn out to be minus .2884 volt, 2844 volts, right. So this is the potential of that half cell. So now when we write EAG equal to E0AG minus 0.0591 log activity of Ag plus. So now we have determined that EAG as minus 0.2844 volts, and this EAG is again minus 0.799 volt. So now when you try to calculate the activity of Ag plus, we write log activity of Ag plus is equal to, we have a minus sign, 0.799 minus 0.2844 divided by 0.059, which is equal to I don't have the value for this, doesn't matter. So from this one can calculate activity of Ag plus as 2 into 10 to the power minus 9. Therefore, activity of chloride will also be the concentration will be the concentration of KCl, that is 0.1 into the mean activity coefficient, that is the value of F, which is 0.77. So we get this value as 0.077. So here the activity solubility product La is nothing but A of Ag plus into A of Cl minus, which you can now do a simple multiplication, 2 into 10 to the power minus 9 into 0.077, which is equal to 1.54 into 10 to the power minus 10. So this is the solubility product of silver chloride determined using the method of EMF measurement. So this is how one can easily determine the EMF of one can easily determine the solubility product of sparingly soluble salt using two different methods, conductometric method and a potentiometric method. So we will continue from here in the next class and talk about how one can determine the dissociation constant of weak acids, weak dibasic acids like oxalic acid. Thank you.